Okay, so welcome to this next video in which we are discussing the mechanism of action of cisplatin, which is short for cis-diamine dichloroplatinum. Okay, right, so we now want to discuss how cisplatin can act on guanine or adenine organic bases. Now, I've discussed the structure of both adenine and guanine, and we know that they both have this very similar N7, and basically this mess over here, which was different between the two, is not going to matter for cisplatin, how cisplatin interacts with them. What it is, actually, it prefers guanine, so it prefers this modification, but the actual way it binds is the same in guanine and adenine. Maybe the affinity is less, but the way it binds is the same. So, I will show the way it binds on guanine, but the way it binds can then be transferred to adenine. Okay, so, here comes cisplatin, which remember is this platinum compound with two chlorine atoms bound, and then these two amino groups of it here. So this is cis-diamine dichloroplatinum. Right, so, what's going to happen is this lone pair of electrons is going to attack, it's going to nucleophilically attack the platinum. Okay, so the nitrogen basically is going to donate both of its electrons into a single bond that it's going to form with platinum. Okay, so this nitrogen is going to make a bond with platinum, and it's going to put both electrons in. Now, when it does that, effectively it donates an electron to the platinum, because if you've got a covalent bond, then the understanding is that one of the electrons comes from each of the participants in that bond. So if there are two electrons in the bond, then the understanding generally is that one of them belongs to this platinum and one belongs to the nitrogen. So in effect, the nitrogen, in forming this double bond, has donated an electron to the platinum. So the nitrogen is going to get a positive charge, and the platinum is then going to get a negative charge. Then, what's going to happen is platinum doesn't like having this negative charge, and chlorine atoms love having a negative charge. So what happens is one of these bonds between the platinum and the chlorine atom cleaves, basically. Now, again, this single bond here between the platinum and the chlorine atom, that will contain two electrons, one from the chlorine atom and one from the platinum atom. So let's draw this. Here's the one from the chlorine atom, here is the one from the platinum atom. Okay? Now, if the chlorine takes both of these electrons, it will have taken back the one that belonged to it, but it will also have taken one that didn't belong to it. It will have taken this one from the platinum. So, the chlorine has effectively nicked an electron off the platinum. So that removes the negative charge that the platinum had gained from taking an electron from this nitrogen. Okay, so the platinum no longer has a negative charge. Instead, this chlorine atom is going to have a negative charge, and it's finally going to become a chloride anion. Okay, so let's draw what's going to happen. Okay, so overall, this is where we go to. We've still got our purine ring here. Okay, so let me draw the purine ring out. So here is this six-membered, whoops, we nearly forgot the nitrogen. Here is this six-membered pyrimidine ring here, which is then bound to the imidazole ring down here. So you have these two nitrogens coming off down here. Okay, let me bring this up. Then what we have is a single bond here, a double bond here. Okay, and then we've got double bond there, double bond here, and then we've got this carbonyl group up here, and this hydrogen off this nitrogen, and then we also have this amino group over here, the H2N group. Now, let's draw this cisplatin bound to it. So here's the platinum now. Okay, then we've got these two amino groups. They are untouched by this binding. So here's one, here's the other, and remember they're still next to each other. Then you've got a chlorine atom off here. The nitrogen still has a positive charge, and this chloride anion over here now has the negative charge. So this is the positively charged ion, here's the counter ion over here. Right, so this is the overall structure now that we have produced. We've produced a guanine with this molecule bound to it. But the thing is, this can happen all over again. We have another chlorine atom off here. So basically what you can do is you can bring in another guanine organic base here. So let me draw one of these. So let's revise the structure of guanine once again. So here is the pyrimidine ring again. Okay, we have a double bond here, a double bond here, carbonyl group off up here, a hydrogen off the nitrogen, an amino group over here. Okay, and then we have the imidazole ring down here, this 5-membered ring with these 2 nitrogens here, an imide bond there, like so. Oops, we missed the hydrogen over here. And then we should have a hydrogen there. Right, now this N7 nitrogen here has a lone pair of electrons. So again, what it can do is it can nucleophilically attack the platinum. Okay, forming a covalent bond with that platinum, where the nitrogen has donated both of the electrons. So the nitrogen has effectively given the platinum an electron, meaning that the nitrogen gains a positive charge, the platinum is going to temporarily gain a negative charge, but then what will happen again is that both of the electrons in this bond will go to the chlorine atom. Now, one electron belonged to the chlorine atom, but the other belonged to the platinum, so effectively one electron goes from the platinum to the chlorine atom, which means the platinum loses this negative charge that it temporarily got from receiving this electron from nitrogen and goes to neutral, and then this chlorine atom is going to gain a negative charge, so it's going to become negatively charged and it will become another chloride anion. Okay, so then what you'll end up with basically is 2 guanine organic bases linked to this same drug molecule, and this is what cisplatin is brilliant at doing basically. It is brilliant at linking together 2 purine organic bases. Okay, so there are some specific combinations that it's fantastic at doing. So, if I remind you of the structure of DNA, okay, so we'll just draw one of the strands of DNA now. We won't draw the 2 complementary strands, because basically cisplatin does not link. In fact, actually I will draw 2 covalent strands to get this point across. Okay, cisplatin does not link between different strands. It links between the same strands. So here's our DNA again. Okay, right, and I will draw a guanine here. Okay, and then we'll have, what shall I have here? I'll have, this is difficult. I'll put, I want to put another guanine here. Okay, now, the problem is I'm not going to actually be able to show what I wanted to show. Well, I'll do it on a simpler picture. I'll talk about this picture in a moment. So basically, if we have a simpler picture which requires less effort to draw, so here are the 2 strands of DNA. So I'm simplifying this sugar phosphate backbone. It's being demoted basically because I fed up of drawing this out over and over again. It's being demoted to just a line here. So let's put some organic bases in. You see this picture's far quicker and easier to draw. So here's our first organic base pair, G and a C. Okay. Then we might have, what can we have next? We'll have C and a G here. Now this will get my point nicely across. So cisplatin is not very good at linking 2 guanine organic bases which are on opposing strands. So it is not good at producing inter-strand crosslinks. Okay, so inter-strand crosslinks are when a molecule binds to 2 organic bases which are on different strands. So basically, cisplatin would not be able to link these 2 guanines here, basically. Okay, so that's a big no-no. Write that down and put a very big cross through it, as Dr. Najib would say. Right, okay. Instead, what it's extremely good at doing is linking organic bases when they are on the same strand. So if you ever have a guanine followed by another guanine on the same strand, like so, so these 2, then it can link those 2 together. In this scenario that I've drawn here, basically, it's very good at producing crosslinks like that. And those are what are known as intra-strand crosslinks because they are within the same strand. So this is an intra-strand crosslink. Okay, right, so it's a very good at producing intra-strand crosslinks. Okay, now we've discussed that it can bind to guanines, and it likes guanines very much so, but it also can bind to adenines. So let's discuss the fact that it can also bind to adenines. Right, so if you look at the intra-strand crosslinks that cisplatin molecules can form, you find that most of them are between guanines, as so. You find, in fact, that 65% of the intrastrand crosslinks that cisplatin forms are between things where you have, well, between points in the DNA where you have this PG as it's called. So why is it called that? Well, basically it's called that because you have a phosphate, then you have, now you might think, well, here's the guanine, how come they haven't mentioned the sugar? Well, basically, when you have a guanine organic base, okay, so when you have the guanine organic base plus the deoxyribose sugar, this actually is known as strictly as deoxyguanosine. However, we're really abbreviating it to guanosine here. It would actually, strictly speaking, be deoxyguanosine, but you'll find people often refer to that as guanosine. Guanosine strictly is ribose bound to guanine rather than deoxyribose. However, that's really what it means here. It means you've got a phosphate followed by a deoxyguanosine followed by another phosphate followed by another deoxyguanosine. So you find that 65% of the intrastrand crosslinks formed by cisplatin is basically when you have two consecutive guanine organic bases within the DNA strand. Okay, so the next most common way that it will, the next most common intrastrand crosslink that you find is what's known as the PAPG scenario, and you find that 22% of the intrastrand crosslinks are of this form, and we're now in an ability to, well, we now have the ability to understand what this means. This means you have a phosphate, then you would have an adenosine, which is adenine, strictly speaking, bound to ribose, but we'll break the rules slightly into it's bound to deoxyribose since we're talking about DNA. And then another phosphate, and then another deoxyguanosine here. So basically, if you imagine turning this into an A, so let me draw one of these cheaper pictures. So if we have an A followed by a G like that, then the second most common link that cisplatin can form is between this adenine and this guanine. So it will bind to one adenine and one guanine in the same strand and produce this intra-strand crosslink. Now, interestingly, it does not, repeat, it does not form crosslinks between P, G, P, A. So instead, if you have the other way round, basically, if you have this guanine and then this adenine, it will not form a crosslink between those two. It has to be the adenine before the guanine. It does not work if it's the guanine before the adenine for some reason. Okay, so 65% plus 22% makes 87%. The other 13% of the crosslinks are other crosslinks that it's more difficult to argue for how those mechanisms actually occur. So other crosslinks is the other 13%, but they're still intra-strand crosslinks. So very, very important that you understand that cisplatin is forming intra-strand crosslinks, where it is forming links between organic bases on the same DNA strand, not inter-strand crosslinks. So that's how it's different to all the other cross-linking agents we've seen so far, i.e. the nitrogen mustards, the nitrosoureas, and mitomycin C. They were all capable of forming inter as well as intra-strand crosslinks. Cisplatin, because it's such a small molecule, is only capable of forming intra-strand crosslinks. So the other 13% are other intra-strand crosslinks. So other intra-strand crosslinks. Right. Okay, so now let's talk about the consequences of the formation of these many different types of intra-strand crosslinks for the cell, and how this is going to have an anti-proliferative effect on our cancer cell. Okay, right. So basically, if you put these you don't have inter-strand crosslinks. If you put these intra-strand crosslinks on your DNA, so basically, cisplatin is given intravenously. It's not something that's given as a tablet. It's not taken orally. It's given intravenously. So the patient comes in for an intravenous dose of cisplatin. And cisplatin basically will go into the cancer cells, well actually it will go into all the cells in the body, and it will form these intra-strand crosslinks within your DNA. Now what's the effect of that? Well basically, what's going to happen is that you are going to stop DNA replication and also transcription. So if I just describe for you what happens in order to make mRNA from DNA. So basically, if we have the DNA here, so here's your DNA. Now in order for transcription to occur, what has to happen is RNA polymerase has to bind to the DNA, and it has to be able to open the DNA, and then it has to read the DNA to make mRNA from it. Okay, so it opens the DNA, and then what it's going to do is it's going to make its way along this coding strand. So one of the strands of the DNA will be the coding strand, and what it's going to do is it's going to synthesize a piece of mRNA which has a complementary sequence of organic bases to this coding strand of DNA. Okay, and if you've got these intra-strand crosslinks within this coding strand, then do you think the RNA polymerase enzyme is going to be able to build a complementary piece of mRNA to this coding strand? Well, the answer is no. So basically, having the intra-strand crosslinks between organic bases on the coding strand of the DNA stops RNA polymerase from being able to synthesize a complementary piece of mRNA. So let's say we've got our two guanines here, and they have this intra-strand crosslink between them. So here's this crosslink. Then that's going to stop the RNA polymerase from being able to copy this piece of DNA into a complementary piece of mRNA. So basically what you're going to get is transcription going down. Okay, so you're going to stop the production of mRNA. Now if you stop the production of mRNA, mRNA is needed to then go through the ribosome and produce protein. So you stop the production of protein. So transcription goes down, protein synthesis goes down. And what effect will protein synthesis going down within all the cells of the body have? Well, if you're just a normal cell sitting quiescently, then will it have any effect on you whatsoever? Well, no, because you're not actually synthesizing any proteins. So it's not going to have any effect on you at all. It's not going to do you any damage. However, if you've got a cell that is rapidly dividing, such as a cancer cell, but there are also examples of physiological cells which are undergoing rapid division, and that's the basis for the side effects of chemotherapy. Okay, so if you've got a cell which is rapidly dividing, then let's just go through the division process very crudely. A cell goes from being one cell to being two cells. Okay, so in cell division, a cell divides into two. Now, for this division process to happen, you have to double the amount of proteins in this cell, because this cell suddenly has to have enough proteins, not just for one cell, but now for two cells. So in order to make the proteins, the increased number of proteins that you need for these two daughter cells, you're going to need functional protein synthesis. So when protein synthesis is inhibited by the intra-strand crosslinks that this cisplatin drug has formed, that's going to stop cell division, because if you can't produce the proteins for the two daughter cells, then you're not going to be able to divide. So this is going to have the effect of stopping cell division. Okay, so we'll continue this discussion in the next video.